So we're still in the CFD topic and talking about discretization. And we would like to touch base with the finite difference method first before we jump into the finite volume method. Let me summarize all what we did learn so far. So in using CFD, you have an original design. This is your idea that you would like to investigate. Then you have to select a governing equation or system of equations. We call that the models, right? And these are, in most cases, are differential equations, right? Then you define your models. Then you will go and apply some assumptions and approximation. And or approximations to make that equation much easier. Then you're gonna do solve. That's in practical, right? So after you do the approximation, you're gonna solve that equation. And we have different approach of solving that equation. You could do that analytically, right? This is the analytical fluid dynamics. You could do that experimentally. This is the experimental fluid dynamics. Or you can do that numerically. And that's what we call the CFD, right? To do that numerical approximation or solution for your model to get whatever results you're looking for, you have to do, let me actually make a big box here. This is our CFD. You have to follow the following steps, right? I'm trying to build a flow chart here to summarize what we are doing. We do pre-processing. Which include the setup of your domain. And you do the mesh or grid of your domain, right? Then the second one is to start solving. To do the solving, you have to feed in the models that you selected, and you also apply the approximation or the assumptions for that model to be able to solve that, right? So you collect your models, you apply the approximations, then your next major step is to do the discretization. And you have three options. You apply the finite difference method, you apply the finite element method, or you apply the finite volume method, right? Then after you do the discretization, you're going to end up of system of algebraic equation. To solve, which means that your next step is to do the solver setup, which usually it's an iterative method, right? Gauss-Seidel iteration could be Jacob iteration, whatever that method you are using, right? Then after you get your results, right, you have to go for the third major step, which is post-processing, which means that you extract your data. This will feed into here. you're going to extract your data, extract, then you do the analysis. Actually, you do the plotting first, then you do the analysis to perform any corrections or optimization of your design. Then you take this input data and go back all the way to modify your design, readjust or revisit the models, make different assumptions, and so on. So this is the flow chart of the process from the beginning. This is your starting point, right? Your design all the way to get your data and to revise or redesign your target. This is just a summary for what we have. Now we are in this portion here. We would like to look to the finite difference method as one of the most famous discretization technique to approximate the differential equation into algebraic equation. So we will put the title here, finite difference method. Finite difference method. Very easy to apply, very simple to do, but again, it only gives you data at the grid points, right? Doesn't tell you what's happening inside each subdomain itself. Let me give a little bit of an example here. Let's assume that you are given a function, looks like this. This is f of x, and this is x. And I don't know what's the formula of this function, and I would like to get an approximation value near a specific point. We call that the base point. So let's assume that you have a base point here. And I know the function value at this base point. Let's call that a, so I know what's f of a. Then I will disturb that base point. So I would like to get the value around that base point. Let's assume that I want to jump to the right a little bit, I want to jump to the left a little bit, and I need to get the approximation value of that function at this point. There are many ways to do that. The simplest way of that to say, okay, let's find that I'm looking for a value of that function at disturbed distance, say at separation distance h here. And I would like to get the value of that function here. The simplest approach, you say, okay, I would assume between these 2 points, I know the value at the base point A, I would like to get the value of the function at distance h measured from that base point. And you say, okay, I would simply approximate the function. I would assume between this point A and this point at distance h from point A, we will have a linear approximation. It seems to be that it really looks good in here because the line is overlapping with that piece of that function between these 2 specific points. So linear approximation is your first. This is assumption, right? And this is all about the approximation here. So I would assume that the function will change between these 2 points in a linear way, right? And if I can get the slope of that function, right, we can find whatever information we need to get, right? So let's get the slope of that line, right? So again, this is, let's call that actually x point x. So this would be x plus h, right? So this is a function f of x. And this, the function value of that point is f of x plus h, and this is what I'm looking for. This is the value of the function here, f of x. Okay, so since we have a linear relationship here, let's get the slope of that line. So I will assume that line has a slope of theta. So tan theta would simply equal to the height over the width. The height here would be the value of the function at the disturbed distance minus the function value at the base point divided by the width here, which is going to be x plus h minus the coordinate x, right? So if you do that, this is your slope. This is the derivative of the function. So this would be simply f dash of the function at the given point x, right? So you simplify the equation here. So f of x plus h is simply equal to f of x plus h f prime of x. So if I know the slope of the function, if I know a value of the function at a base point, I can predict the value of the function at a disturbed distance slightly forward of the base point. That's what happened here, right? So this will give you the function of the value by knowing the slope of that line or the slope of the function at the base point x. Remember, x is your base point. So the function at the base point, the slope of the function at the base point, then the distance or the grid size that we're going to set up later on, I can predict the value of the function. And again, the slope of that straight line is simply f of x plus h minus f of x simply divided by h, right? And because the linear relationship was based on a point that forward to the base point, we call that actually forward method. Because I can set up the slope of the line not by picking a point forward, but if I pick a point backward, I can get the same results, right? So if I pick the value, so again, here's a function. Here's my base point x. Then I'm going to go up. This is the value of the function f of x. Okay, then if I'm looking for a point here, this is distance h again. So this becomes x minus h. I would like to get the value of the function at f of x minus h, right? I will assume there is a linear change here. Again, this is my approximation. You will find that the slope of that line, theta, tan theta, or f prime at the base point, right, is equal to f of x minus f of x minus h. So this will give you this height here, f of x minus f of x minus h, divided by the separation distance, which is x minus h, right? So if I do that, what I'm getting out of this, I'm getting the f of x minus h, it's equal to f of x minus h f prime of x. So we call that actually the backward method because you constructed the linear relationship using the base point and a point backward to that base point. So you can actually use a forward point, so we call that the forward method, or you can use a backward point, so that's called the backward method, right? Another way to do that is, okay, I'm gonna actually do something different here. I'm gonna take that function. This is my base point x, and this is the function f of x. I would pick up 2 points, actually. I would pick a forward point at a coordinate x plus h, and another point at coordinate x minus h. So this is f of x minus h. The function here will be f of x plus h. Now I can fit the selected point in a linear relationship, and the approximation could be also valid. In this case, my base point is centered between 2 points, one forward and one backward, right? Then if you do that, you can easily get, let's get the slope of the line. It's going to be f of x plus h minus, I'm getting the slope of that line here. This is your angle theta. So I'm getting that distance here, minus f of x minus h divided by the distance here, which is x plus h minus x minus h, you will end up having f of x plus h minus f of x minus h divided by 2h. This will give you f dash of x. Then you can simply get f of x plus h of your interest. So because I used 2 points here, this is called the central method. You may think that, oh, why I'm picking h minus h? I can take h over 2, like a small distance, minus h over 2. It will lead to the same answer here. So, but you will end up having, instead of having 2h, the width of that triangle, it's going to be only h. But again, this is just an approach how to find an approximation of a function using that linear approximation thing. This is not really coming from nowhere. This is simply coming from Taylor series. Taylor series is a mathematical way to approximate a function near a base point, a disturbed function near a base point. So if you recall Taylor function, Taylor approximation is a formula we use to approximate a continuous domain into to predict a value of a continuous function near a disturbed base point. So Taylor expansion is the function of x plus h. It's equal to f of x plus h f prime of x plus h squared divided over 2 factorial f double prime of x plus h cubed over 3 factorial f triple prime of x. So actually Taylor series or Taylor expansion goes beyond the linear approximation. We did that by approximating the equation to linear, but you can approximate between the 2 points in a higher order, so you can actually go for the second derivative and third derivative and so on. So that's the beauty about Taylor approximation. So we did manually the linear approximation, but Taylor can be used for higher order approximation as well. So we use that Taylor approximation to where that finite difference is coming from. It's coming from Taylor approximation. That's how it is actually developed. So why I'm introducing the Taylor approximation? We know that linear approximation can be done without using Taylor by picking up the 2 points, getting the slope of the line, as I did in the previous sheet here. Either you are using the forward, the backward, or the central method, finite difference method here. But why we really need Taylor approximation? Because Taylor will tell you, based on the approximation, what is the order of the error. Again, we are approximating the function. We need to know how much the error. So for example, let's do the backward finite difference method, right? So in the backward finite difference method, let's do that using Taylor approximation. So it will tell us what's the error. So this is the function f of x, and this is x, and here's how the function looks like. Here's my base point here, x. I'm going to pick another point here, backward, x minus h. So I went backward. And this is a function I'm looking for. This is a given value at the base point. So let's apply actually the that Taylor approximation to get the value of x minus h. So what I'm going to do, I'm going to say that f of x minus h. What you're going to do, you're going to replace every h in this equation by minus h. That's the simple way to use Taylor approximation to get that value. So I will say that this will give me the f of x minus, I would take h and put minus h. So that's minus h f prime of x plus, I will remove h and replace, so h will be replaced by minus h, but I'm still h squared, so it's going to end up to be plus h squared over 2 factorial f double prime of x minus h cubed over 3 factorial f triple prime of x, and so on, right? So when we do the finite difference method, it's a linear approximation, which means that I will cut my approximation up to here. So f of x minus h equal to f of x minus h, f prime of x plus something, right? The rest of the terms, right? So if I would like to get f prime of x, why I'm looking for that? I'm looking for f prime and f double prime. Most of the differential equation is presented in the first and second derivative form. So what we are trying to do here is to find the approximation for the f prime and f double prime. And this is what I did here. I can develop a relationship or a correlation for the f prime, for the f prime, for the f prime. Either you are using forward, backward, or the central method, right? So that's what we're trying to do, is to find f prime, f double prime, and more if needed, to approximate your differential equation or to convert your differential equation into algebraic one. It's an approximation. And you realize that the approximation is coming to be a function of discrete points, right? So there's no derivative in the function here. There's no derivative here. There's no derivative here. So this will remove the slopes and the second derivative and so on by just discrete values, which will end up having algebraic equation at the end. So that's the idea behind it. So we are now using Taylor, the more generalized format, to approximate our derivatives, right? So if I'm looking for the first derivative here, I will isolate that term to the this side. So I will have f prime of h will equal to f of h minus, f of x minus h minus f of x divided by h plus more. Let's recall what term was here. There was h squared over 2i f double prime of x, right? Regardless of the sign, you will end up having something here, but because I divided by h, it will be an order of h, whatever it is. So what's telling me that the backward finite difference method approximates the first derivative f dash of x by the function of f of h minus x times minus f of x divided by h, and we will have an error of an order h. So the beauty of using, the first advantage of using Taylor approximation, it can give you the order of the error. This is what you terminated. This is the remainder that you ignored because you are only going for the first derivative of the function that way, right? So the smaller the value of h you are using to discretize your domain, the smaller the error that you're going to get from that approximation. Okay, that's the key. So what about if we try to get actually the second derivative? Can we get the second derivative using the backward? I'm still in the backward method. So what I'm supposed to do if you want to get the second derivative from the backward? So if you want to get the second derivative, what we're going to do, we're going to pick actually second derivative. It's a higher order. So I'm going to do, to develop that second derivative, I'm going to pick up actually 2 points. That's my base point x. I'm going to pick a point at x minus h, and I will pick a point here at x minus 2h. Okay? Now, let me get actually f. So let me write down that here. What about f double prime? To get the f double prime, I picked 2 points. This is a function f of x, and this is the x variable here. So I'm going to get f of x minus h. What you will get out of this equation, I will get f of x minus h, f prime of x, plus h squared over 2 factorial f double prime of x, minus h cubed over 3 factorial f triple prime of x, plus blah, blah, blah. Let's get f of x minus 2h. I will have f of x, simple language. You take every h value in the Taylor series and you replace it by 2h, negative 2h, right? So what you're going to get, I will get f of x will remain the same, plus h will be minus 2h f prime of x. H will be minus 2h, minus a square will be plus, 2 square would be 4, so I will have plus 4 h square over 2 factorial f double prime of x minus 2h cubed, negative remains, 2 cubed, that's going to be 8 h cubed over 3 factorial f triple prime of x plus blah, 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 right? Now, let's get actually the, let's actually subtract f of x minus 2h minus 2 f of x minus h. So I'm going to multiply this equation by 2, all terms, then I'm going to subtract this minus this. What we're going to get? You'll get f of x minus 2 f of x. So I will get minus f of x. I will get minus 2h f prime minus 2h f prime, f dash prime, it will cancel out. So the idea, I would like to get a pure relationship in f double prime without having f prime. So I'm canceling f prime out of this. So the reason I multiplied by 2, then I subtract to cancel out the f prime. Then let's look to the double prime. I will have, this is 4, 2 factorial is 2, so I'm going to end up having here 2h squared minus, here I will have 2 times h squared over 2, 2 will cancel out, so I'll have only 1. So I'm going to get 2h squared minus h squared, so I will get actually plus h squared f double prime of x. Then if you continue, we'll get actually h cubed. Again, this is 8 over 6, right? Which is 4. I will divide by 2, so it's 4 over 3. Then this will be actually 1 over 3. So when you subtract 4 over 3, negative, plus 1 over 3, it will be minus 3 over 3, which is 1, f triple prime of x plus the rest of the terms. Now, I would like to isolate f double prime, so I have to divide all terms by h squared. I have f double prime of x will equal to, this will remain in this side, everything will go to the other side. So I will have f of x minus 2h minus 2 f of x minus h plus f of x divided by h squared. This term will come to the other side, will be plus. Then h cubed will be divided by h squared, so I will have the error of order h. So this is the formula that you can approximate f double prime using the backward finite difference method, and you will have an error of order h. Okay, so that's simply how you derive the relationship for the f prime, f double prime, using the Taylor expansion to get the approximated value or the approximated function plus the expected level of error that you end up having the approximation method. Same way, you can actually prove to develop the f prime, f double prime using the forward method. So instead of having x minus h, you will have a point to forward, x plus h. For double prime, you will have to add 2 points to the right and follow the same steps. Then you can find the error of the forward and central method as well. And then you can figure out which method I should use. If all of them, they can lead to the same approximation, but if one of them has an advantage in the error improved, I would recommend to use that method. When you do that by yourself, you will figure out that which one is improved. You should get a better improved error when you do the central finite difference method. So if you assume 1 point to the right, 1 point to the left, then you develop the formula for the f prime, f double prime, you will see that that error actually will be improved because it will be a higher order of h. I think that you should practice that yourself and figure out what is the error you can get for the forward and the central finite difference method. that would include the introduction of that part for the finite difference method. We can actually generalize it, as we can see later on. We don't use x and x minus h, x plus h, but we will use a language that's slightly different for the CFD analysis. We will set up the coordinate in the form of I and j all the time, and use that. So let's see how we can do that. Then we will jump actually into some examples to recover the use of the finite difference method in solving very simple problem, simple heat conduction problem. That's where the finite difference fits well for that part. So let's see with that in the going part.